Hi, everyone. So welcome back to section. Hoping everyone had a good time this week and did well on their problem set, the mission one. Happy to answer any questions tonight, and we can go over the material from last week. And if anyone wants to go over some material for this new module, we can do that as well. Happy to answer any questions, and hopefully we'll have a helpful discussion tonight. Did anyone have any issues with any of the coursework this week that I could help cover?
Nope.
Okay, so I'm just going to pull up a presentation. How was the assignment? Was the assignment okay?
It's pretty easy.
Good. Glad to hear it.
I did okay on it. I got 19.
Great. So it sounds like you guys have been doing well on it so far. Okay, so just so we're on the same page, here we are. We just submitted the first assignment, and we completed the numerical data module. So then so here's the textbook readings that everyone should be reading, and we'll be covering probability tables and relative risk. And that will be covered in the next assignment, which will be due next week. So just to give everyone an idea of the schedule. So from here on out, you'll have an assignment that will be turned in each week by Thursday. After probability, we'll do correlation analysis, simple linear regression, basics of sampling. You'll have a break for spring break. And then we'll have the first exam, which will cover everything that we covered up until that point. So if nobody has any questions about the material we've covered already, I can start going over the probability lecture with everyone. And we can get a head start for the upcoming module. So here's where we are in the course map. So we'll be going over probability tables and relative risk now. So we broke it down into 3 parts: proportions as probabilities, working with probability tables, and relative risk and conditional probability. So just so everyone is aware, if you haven't studied probability before, it can be a tricky topic for students. I frequently find that a lot of students, either they get probability or they struggle with it, and it's something that's a difficult topic for them. So if you are having trouble with this material, feel free, you have to, be sure to reach out and ask for help, because students definitely can have trouble with probability. And don't be afraid if it's tricky, because it's a tricky topic to learn. So basically what a probability is we can think of probabilities as a proportion, the proportion of an event happening that we can say is either, so depending on the field that we're looking at, it's basically the idea of whether an event is more or less likely to occur. So here we're going to use an example with health insurance. And suppose you're a public health researcher and you're interested in why some people don't have health insurance in the United States. So that's what we're going to be working on in this case. And we're going to look at a case study, a data set of people in the United States who have health insurance, and we have some other variables on them, whether they have health insurance, whether they don't, and we're looking at how likely are Americans to be uninsured. So this is how the data set looks like if you pull it up in R. So this data set is available on the course website. It's called the Employed ACS data set. So as you can see here, we have different variables up top. We have both categorical and we have numerical variables. We have sex, which is a categorical variable, and then we have age, a numerical, married, income, hours per week, this is how many hours they work per week, their race, whether they're a US citizen or not, whether they have health insurance or not, whether they're poor or non-poor, and whether they're considered to be a young adult or not. So as we can see here, we have how many numerical variables? Age, income, also hours per week, and so we have 3 numerical variables, and the rest are considered categorical variables. Is everyone clear on that? So what we can do is we can simply create a table of proportions for those who have health insurance and those who do not have health insurance. And we can do that with a simple command in R, which we give to you in the next PSET R code. And here it'll give basically a table that will count how many people have health insurance and how many people do not have health insurance, and it'll have a margin total here, which is 343. So this can be represented not only in absolute numerical values, but also as a proportion out of the whole by setting 343 as 1 or 100. And then 303 divided by 343 will be 0.88, which can be represented as 88%. And 40 out of 343 will be 0.12, so 12%. So what this means is that 88% of the people in this study have health insurance and 12% do not. So if we were looking at the probability that a random person in our study has health insurance, that would be an 88% chance that a person chosen at random will have health insurance amongst our data set here. And then likewise, if they didn't have health insurance, that would be 12%. So likewise, we can also ask, given that you are poor, economically poor, how likely is it that you will have health insurance? So that's basically like a conditional probability. And basically here we're giving you some introduction into probability as a theory, as a discipline, which has been discovered hundreds of years ago. And so it was discovered in 1654 by two famous French mathematicians. And it was basically discovered over a dispute in gambling. So we had a question of what a conditional probability is. So that's a great question. So we're going to get to that. That's actually in part 3. What a conditional probability is it's taking a probability that's conditioned on a given state. So to explain it, we can say, what is the probability? And it's very often used in medical and biomedical statistics. So just to give you an example, is we can take the probability that someone will get lung cancer. We can say that amongst Americans, the probability of getting lung cancer might be 1%, right? But if we condition the probability on those who are smokers, who are active smokers, so that means that we're looking at specifically the smokers within the United States, what the probability of them having lung cancer is, that might be a much higher probability because it's conditioned on the smoking status of the individual. So that might be a 35% probability of getting lung cancer. Does that make sense, Andre? That's what a conditional probability would be. So in this case, what the example was we were looking at those who are economically poor, whether they are more likely to not have health insurance. So that's what I was saying would be a type of conditional probability. And just like I was saying earlier that, probability can be a bit tricky. It can be, oftentimes it can be counterintuitive. And sometimes it runs counter to our emotions or our sense of intuition. And just to give you an example is you'll see this a lot with casinos, is if you've ever been to a casino and you've ever seen that roulette wheel and you've seen the screen on top that shows you in the past what the different what the ball landed on, whether it was black or red, and the different numbers, and that influences people. That influences your emotions and your intuition. So you might say that if it landed on black 10 times in the last 10 times, you would think that maybe it's time for it to land on red for the next one. But actually, probability speaking, that's not the case. Each and every time you roll that ball, it's considered to be an independent event, and none of the past events in roulette will influence any of the future events. So that's something that the casino actually does to use that, again, to use this counterintuitive measure, to use that to their advantage, because they have that screen on the roulette wheel. So people will look at it and think that since the past will dictate the future, but that's actually not correct. And we know that through probability. That was actually probably one of the arguments that led to the discovery of probability back in the 17th century. So probability is the measure of uncertainty or how likely an event is to occur. So you have an event, and you can think of, let's say, a coin flip. So a coin flip, it's an independent event, and the coin can either land on heads or tails. So there's two outcomes, and it has to be one or the other. It can't be both. You can't flip a coin one time and get both the heads or tails. It has to land on either heads or tails. So that is to say that the two events are mutually exclusive. So that's an example event, is we can find what the probability of getting a heads is when we flip a coin. And because there's two choices, heads or tails, the probability of getting heads is 1 out of 2 or 50%. We can also look at some other examples of probabilities, like eating trans fat, how likely that would be to give you heart disease, or will working more than 40 hours a week lead to depression? So I use some terms here, and you might not be familiar with those terms, but here we can go over them. Each probability event is a random event in that we don't know the outcome of that event. So when we flip a coin, we don't know whether it's going to be heads or tails. That's why we're calculating the probability or the odds of it being one or the other. And like I said, flipping a coin, it has to be either heads or tails, and there's no other there's no other outcome of that coin toss. So that means it's exhaustive, because it can only be heads or tails. It cannot be some other outcome. That's what exhaustive means. And it's also mutually exclusive, which means that if we flip the coin and we get heads, that means that it can't also be tails. It has to be one or the other. These are mutually exclusive events that you can't have it both ways, in other words. So here we have the properties of outcomes, that we have collectively exhaustive events, so that we can actually list out what the different outcomes are. So in other words, with the coin flip, we have either heads or tails. Mutually exclusive, we went over. And sample space is a notation we can use to denote the probability of a given event. So we have a sample space is equal to the outcome 1, outcome 2, etc., up to outcome k, where k is your possible outcomes. So you theoretically could have an infinite number of sample space, but we're not going to go into those examples. All of our examples are going to have finite sample space. And this is just to illustrate that point, that we can theoretically have a limitless amount of options, but we're not going to be covering that. And just to illustrate the point that you have to have mutually exclusive events, you can't both gain and lose weight at the same given time, and that we can quantify them. So there's a lot of notation used in probability. So when we talk about the probability of an event, we usually denote it by having shortcuts. So we, instead of writing probability of an event, which will take a long time to write out, we can simplify that by just shortening it to probability of A, the event A, which we can shorten to be PRA or P of A. So if you see any of these notations, they all mean the same, and they all mean the probability of a given event A. And what we define that is the chance that A will occur. And we say that it will be a number between 0, which is absolutely no chance of occurring, to 1, which is absolutely certain that it will occur all the time. So your probability A will be somewhere bounded between those two numbers. It can't be less than 0. It can't be more than 1. It has to be between those numbers, or 1 or 0. And in order to calculate the probability, is we can take the number of trials in which the event did occur over the total number of trials. So for instance, say you didn't know whether the probability of flipping a coin was 1/2. Say you actually did not know that. You could actually test that. You could take a quarter out of your pocket and you could flip it up in the air once, right? And then you'll see if it's heads or tails, and you'll make a list, and you'll write the number of times you flip the coin and whether you got a heads or a tails. So say you flip the coin 20 times, for instance, you might get 12 heads and 8 tails, right? So if we were curious on what the number, the probability of getting a heads was, and we said it was 12, right? 12 heads, and we flip the coin 20 times, you would divide that 12 over 20, and you would get a 0.6, or 60% probability. So that's true, right? We know that the actual probability of flipping a coin and getting a heads is actually 0.5 or 50%. But doing an experiment you can get any number of different heads and tails, right? So how do we explain that? Well, the reason that is because when you have a small sample size or a small number of trials, you're not going to get to the true probability. So in order to do that, we're going to need a much larger sample size in order to find what the true probability is. So if you flipped a coin, 20 times, you might, it's very feasible for you to get 12 heads and 8 tails. But if you flipped a coin 100 times, you might get something closer to 50 out of 100. And then if you flipped it 1,000 times, even that much more closer to a 50-50 probability. So does that make sense to everyone on how you calculate probabilities? Great. So like we said, the probabilities are going to be between 0 and 1. And if you're at 1/2, that will be an even chance. So flipping the coin is a 50% probability. So that means that the probability is 1/2. It's completely even. So we could also denote probabilities as odds, which is denoted like this, which we can say is 1 to 1. So that actually is the same thing as saying 1/2, because the probability of getting a heads and tails is equal. So we call them to be 1 to 1 in this notation here. So now we can actually state some rules of probability. So rule number 1 is a probability is a number between 0 and 1 inclusive. Okay, so that means that it has to be a number that's between 0 and 1, and it can include 1 and 0. It just can't be outside those two. And we said that events are denoted by capital letters, and they're never above 1 and below 0. The second rule of probability is that the set of all outcomes must be 1, where S refers to the sample space of all possible outcomes. So all the possibilities have to add up to 1. We can't have a probability, we can't calculate a probability if we're going to say that it adds up to 2 or something. That's not the convention of calculating probability. So for all our probabilities, for the purpose of calculating, we have to make it equal to 1. If we don't have it all equal to 1, then we're missing either a possible outcome, or we're having 2 possible outcomes that could happen at once, which is violating the principle of mutual exclusivity, like we said earlier. So that's the principle that if you flip a coin, you can't get both heads and tails at the same time. Now, the third rule is called the complement rule. And the complement rule says that the probability of not A, and that's what this little hat on top of the A says, is the hat on top of the A means not A. The probability of not A is equal to 1, because 1 is the total options here, right? So if we have the probability of heads or tails, they would both equal to 1. And let's say probability of A is heads and probability of not A is tails. If we wanted to calculate the probability of not A, we could just take 1 minus probability of A, and then we're left with the other probability. So in this case, the probability of getting heads is 0.5. So 1 minus 0.5 is 0.5. So that's an easy example, but in other examples, you might not have a 50-50 1-to-1 probability where you can calculate the complement. So this is just a funny little cartoon that says there are those people who can read Venn diagrams and those who can't. And this is showing that there's mutual exclusivity here because there's no overlap. So if there was any overlap, that would violate the principle of mutual exclusivity, because you can't both read and not read Venn diagrams at the same time. So here's how a Venn diagram works: is we have the probability of the sample space, which is equal to 1, probability of A, which is a number between 0 and 1 inclusive, and the probability of not A, which is outside the circle, is 1 minus the probability of A. So like we said before with this health insurance example, we had 12% no, 88% yes, and they added both up to 100%. we can view these as mutually exclusive and collectively exhaustive outcomes. So that the sample space is they either have health insurance or do not have health insurance. And if you add them both up, we get 1. And if you subtract one from the other, we get the complement. Okay. I actually just I have to take a 5-minute break. I just have to take a phone call, and I'll be right back in 5 minutes. If anyone has any questions, feel free to discuss amongst yourselves, and I'll be right back. Okay, really sorry about that, guys. So here we go. So it says, so basically, that was basically the gist of probabilities, but we want to be careful as well, because there was this one statistician, this math tutor, who tried to calculate his odds of finding a girlfriend, and he calculated it to be less than the probability of finding aliens, right? He said that the probability of finding a girlfriend was very, very, very small, 0.00000035. So that's much, much less than 1%. Basically 1 in 285,000. And he defeated his own odds. He actually is now getting married. He calculated that there were basically only 26 women for him in the United Kingdom, but despite those odds, he actually found his fiancee Rose, who ticked all his boxes. So where do probabilities come from? They can come from three different ways. There's either the empirical or experimental method, the logical or the classical method, and a subjective or personal. So basically, the subjective probability, that's not really based in empiricals. So that can be based on anecdotes. Empirical is based on a set of data. So as we discussed, we can calculate it using this formula. But there are limitations to empirical probabilities. The most common way to assign probability values is with the empirical method, but it may be misleading if you base the probabilities on a small set of trials. So like we said earlier, if you were to flip a coin 3 times and you got heads 3 out of 3 times, it's very possible. That's not an impossible event. You would then conclude that the probability of obtaining heads is a perfect 100%, which we know is not true. And that could actually lead to a manifestation as an anecdote. So it's very possible that you might hear someone say they know 3 people who smoked every day and lived well past the age of 90. Well, that's just an anecdote. And I'm sure if we put it to the test of an empirical trial, that it wouldn't pass that muster. So next we can have the logical approach, which is based on the number of outcomes in which an event occurs over the total number of possible outcomes. And it requires that each of the possible outcomes are equally as likely. So for instance, we can use the probability of flipping a coin, which is 1 to 1, or the probability of rolling a fair dice, which is 1/6 for each of the different possibilities, because there's 6 sides. And there's limits to the logical approach as well, because we assign probabilities to basic games and assuming that they're fair games, right? So that the coin is fair. It's not weighted one way or the other. And most situations don't fall under these situations. So it's really kind of limited to these uses of gambling or basically calculating gaming odds. And the subjective method, it's really assigning based on one's belief or judgment. So the probability of an event is basically based on your beliefs. It's not really based on any evidence. It might be, but there's no guarantee. Of course, this is going to have the most limitations. So basically, just to sum it up, probabilities are a way of saying how likely or unlikely an event is to occur. They may be obtained in these 3 ways: empirically, logically, or subjectively. And we obtain them from data when dealing with real-world phenomena. And they work no matter how we obtain our probability values. The basic probability rules. So here we're going to be working with probability tables again. With the same data set, and we have a table of unconditional probabilities. So we can make a table, and what we can call them is so here we go. If we're considering 2 events, A and B, we can also calculate the probability of A and B occurring together, which is denoted as probability of A and B. So 2 events are joint or mutually inclusive if the occurrence of one event is compatible with the occurrence of the other. That is, they can both happen at the same time. But 2 events are disjoint or mutually exclusive if the occurrence of one is incompatible with the other. And that means they cannot both happen at once. If events are disjoint, then the probability of A and B is equal to 0. So here are some examples of joint versus disjoint events. Disjoint, remember, is mutually exclusive. It cannot happen at the same time. So we said flipping a coin. Joint events would be that you can have a birth year of 1985 and draw a card that is king, because one thing does not have anything to do with the other. And this is how it would look in a Venn diagram. This has joint probabilities. As you can see, there's an overlap here in the green region. So why would we use joint events is the question. We would use joint events because there are probabilities where one event can affect the other. So like before, we spoke about having lung cancer and being a smoker that could influence you. So so here we could look at the probability of. So let's use another example for this joint probability. So yeah, so it's kind of like a conditional probability, but let's use a different example. Let's look at this Venn diagram example here. We could look at students who are in Stat 100, and we could look at another in this yellow group. We could look at students who are taking Government 100, and we want to know the probability of students who are taking both courses, stats and government. So we can put it in this Venn diagram, and we can calculate the joint probability, which would be that green region, who would be students who are taking the both courses. So that would be an example of a joint probability. An example of a disjoint probability would be, students who would be that there would be no overlap whatsoever. So it's just illustrating those two examples. So a disjoint example would be that you're born into a wealthy family or you're born into a poor family. You can't be born into both families at the same time. Does that answer your question? Does that clarify things a little bit? Can it be both, disjoint and joint? No, it would have to be either disjoint or joint. You can't have an example where it's both. So to give an example, like we said earlier, a coin flip would be disjoint. An example of a joint example is, here's an example of being born into a wealthy family and working as an investment banker. That's a joint probability because you could have both occurring at the same time. A disjoint example would be something where you cannot have the two probabilities intersecting at all. So there's a difference in calculations, and you'd have to think about it intellectually, whether an example is disjoint or joint. Right. So it's both how you interpret it and also how you calculate the different probabilities. But great questions. So here we talk about working with joint probabilities. So here in the shaded region, we have the probability of A in the blue, and then in the green, we have the probability of both A and B occurring at the same time. And then here on the right, we have the probability of A and not B. So we can say that the probability of A is equal to the probability of A and not B plus the probability of A and B, so that we can fill in this entire circle here. So here, if we wanted to calculate the probability of A, and we see that probability of A and not So here we can look at the probability of A and not B, which is 0.15, and the probability of both A and B, which is 0.2, and we can add those two up to get 0.35, which is the probability of A in total. So here we see that the probability of A is 0.35. Okay. Can you hear me now? Hopefully you can, the audio is back now. I think there might be an issue with my connection. So here in this example, we can use a contingency table of counts for our two variables, which is shown down here below. So here we were looking at the question of whether someone is poor or not will influence whether they have health insurance. So on our axis up top, we have health insurance, and we can differentiate it between people who do not have health insurance and people who do have health insurance and the total. And then on the left here, we have those who are poor and those who are not poor and a total as well. And here we can break them down into these different categories, and the sum of all of them will be 343, as it was earlier we saw. And then we can also look at these margin totals as well. So 40 people did not have health insurance, 10 of them are poor, 30 are not, or sorry, 10 of them are not poor, 30 are poor. 303 people have health insurance, and 203 of those are not poor, and 100 of those are poor. So here, now we have what's called a contingency table of counts. The events listed horizontally as well as vertically are mutually exclusive and collectively exhaustive. So because it fits those rules for probability, we can then divide each of the numbers in these different cells by the total number of people in this study, which was 343, and we can find the probabilities and create what's called a probability table. So by dividing it all by that number, we get 1 to represent the total amount of people of 343 people. And then we actually can represent the different probabilities here. So the probability that someone is poor and does not have health insurance is 0.09, as you can see here, out of 1. The probability that someone is not poor and does have health insurance, so you can see here, is 0.59. The probability, and we also went over before that we said that 0.88 was the probability of people who had health insurance, and 0.12 the probability that they did not, and that adds up to 1, which is our total. So a quicker way would be to simply create a table of unconditional proportions using statistical software such as R. So that would basically, once we learn the command, we could just put that in, and R will present us with these probabilities in this probability table, so that we don't have to go in and do all that division by hand. And then here we can look at the marginal probabilities, which is the margins here. And we make sure that they add to 1, as we said, which they do. Both these margins and these margins both add to 1. If they don't add to 1, you know that you must have made a mistake somewhere, because as we said, they all have to add to 1. So these numbers, this 0.59, these are joint probabilities like we were speaking about earlier. So here, like we said, it's representing the probability that someone is not poor and they have health insurance, because they're both occurring at the same time. And if we sum all of these probabilities, we will also get 1. So that will always be the case. If it's not, it means you did something wrong and you gotta go double check it. So our research question was, overall, how likely are Americans to be uninsured and economically impoverished? And from our probability table here, we can see that the answer is 0.09, or 9%. So next we'll talk about the addition rule. So the addition rule is important because of joint probabilities. Here we learned about how to calculate the probability of both A and B occurring. Now we're going to learn how to calculate the probability of A or B occurring. And the addition rule says that the probability of A or B occurring is the probability of A plus the probability of B minus the probability of A and B. Okay. And this is important because we have to use this when there's a joint probability. And we want to know the probability of at least one of the events occurring. Just some tips about notation is we could say that the probability of A or B could be denoted like this with a little u. which represents or, the union of the two sets. And then P, A, and B is represented by that same U, but upside down, and it's representing the intersection of the two sets. So just so you see that and you're not too confused. And here we can look at the addition rule as a Venn diagram. So here we see there's disjoint probabilities, and if you want to calculate the probability of A or B, that's pretty simple because there's no overlap, so we could just simply add the probability of A in this blue circle plus the probability of this yellow circle, and that's it, because we're not subtracting any overlap because there is none here because they're disjoint. In this case, we do have joint probabilities, and the whole idea of the addition rule is we don't want to double count this area that's shared. So in order to find what the probability of A or B is, we would take the probability of A plus the probability of B, and we'd subtract out this intersection, the probability of both A and B. All right, so that's the addition rule. I hope it makes sense. I think with practice, it'll definitely make more sense if you're confused. I'm happy to answer any questions if you have any questions on the addition rule. But the whole idea is we don't want to double count this green region, the joint probability of A and B. So we're going to subtract that out, because if we don't, we'd get a number that would not add up to 1. It would add up to more than 1. So that's the reason behind the addition rule. So here we can ask you, what is the probability of living in poverty or having no health insurance? So the probability of being poor or no health insurance is the probability of being poor, which is 0.38, plus the probability of not having health insurance, which is 0.12. And then you have to subtract out the joint probability, which is the intersection of the two, which is the probability of being poor and not having health insurance, which we said is 0.09. So if you do that, if you do 0.38 plus 0.12 minus 0.09, you get 0.41. So we could say that 41% of people are living in poverty or do not have health insurance. That's how we can understand this data. If we're looking at either of those two risk factors, we can say that there's a 41% chance. So that represents these different vulnerabilities. So from that 41%, you can conclude from this study that there is a fairly high probability that Americans are socioeconomically vulnerable. It's a good amount of people, 41%, they're either poor or do not have health insurance. And the probability of having extreme socioeconomic vulnerability will be 9%, and that's being both poor and not having health insurance. So those are the people who are at the most risk. So some things to know, some takeaways are that contingency tables can be converted to probability tables, as we saw. The cells will give you joint probabilities, while the margins will give you the marginal probabilities. And the addition rule can help us answer questions about at least one event occurring. And then, so we're basically almost done with this lecture. We just have one more part, part 3, which is on relative risk and conditional probability. So we can quickly go over this, and then I'm happy to take any questions. If anyone has any questions, feel free to stop me, and we can go back and take a look at it. But we're almost done with this, so you guys are going to be in really good shape for this upcoming week. So relative risk is a measure of association. So we can look, the whole idea about relative risk is we're looking at a risk, something that's a vulnerability, and we're looking at an event, an outcome from that. So it's typically used in, again, the medical literature in biostatistics. So we can use the example of smoking and lung cancer. We could say that those who smoke, if they have a relative risk of 4, that means that they are 4 times as likely to develop lung cancer than those who do not smoke. So that's what a relative risk represents. But we could also use it within the humanities, and we can use it to look at something like poverty. And poverty would be the exposure, and then we can say, let's say health insurance would be the outcome. So we could say, though, if you have a relative risk of 2 for that, we could say those who are poor might be twice as likely not to have health insurance than those who are not poor. That's an example of a relative risk. So here we go. Let's look at this. Here are the unconditional probabilities in the margins. Here are the conditional probabilities within the table. And we spoke about conditional probabilities, which conditional probabilities will use the term given. So whenever you see given in probability, you know that it's setting you up for a conditional probability question. So given that we know B happened, what is the chance that A happened? So if you're overweight, given that you're overweight, what is the chance that you'll have diabetes? That's a conditional probability because it's looking at those who are over diabetes in those specifically who are overweight. And then we have a few more examples here. So that should help clarify what conditional probability is. It's subgrouping the amount of people that you're looking at for a given probability. So this is how we denote conditional probability. We have probability of A, which is the event of interest. And this solid vertical line means given B, the conditioning event. Given that B occurs, what is the probability that A occurs? That is what we're looking at here. In order for conditional probabilities, we should consider whether we're dealing with independent or dependent events or not. So that is to say, whether there's any dependence or not. So if two events are independent, if the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B. And if that's not true, then you have dependent events. So that's mathematically how to determine whether we have independent events or not. And independence is essentially equivalent to saying that one event occurring does not give any information about whether the other event occurred or not. And that's informative to us. So to give you an example, we could say, something that might be a dependent event is saying that, to give you an example, a dependent event would be given that someone, sometimes when you're looking at couples and you're dealing with a married couple and you're doing some kind of survey with them, we would consider them to be dependent, one person's results to be dependent on the other because they're within the same household. An independent event would be sampling people who don't know each other and a random sampling of people. To give you another example is if we were looking at vision data and we were sampling someone's vision in each eye, that would be dependent because it's on the same person. So what happens to one eye might be happening to the other eye. That's dependent. But if you're looking at the vision of random people, that's independent. So those are some examples of independence versus dependent events. If you have independent events, it's very easy to find the joint probabilities. You just multiply the unconditional probabilities together. So that's to say, if they're independent, the probability of A and B is equal to the probability of A times the probability of B. But that's a very strong assumption because events are rarely independent in reality. And then we can talk about the multiplication rule. The multiplication rule for joint probability of an event is given by the probability of A and B is equal to the probability of A given B times the probability of B, or similarly, we can just reverse it. It would be the same case. And we can use this rule to help us find joint probabilities when we have conditional and unconditional probabilities. So if you have independent events, it's actually much easier because if you have those independent events, you're not going to have to deal with these conditional probabilities. So it's just simply multiplying the two. But if you do have conditional probabilities, we can calculate the conditional probabilities using this formula. Probability of A given B is equal to the probability of A and B divided by the probability of B. Or similarly, probability of B given A is equal to probability of A and B divided by probability of A. And this will will allow you to calculate conditional probabilities. So again, this is another way of showing that in notation. And this is if you have independent events, you don't have to worry about the conditional probability. You can just multiply the two and divide. So if you have probability of A given B, it's just going to equal probability of A. And here's just a warning to keep track of your events, because the probability of A given B is not the same thing as the probability of B given A. So that's a big mistake. That's very easy to make by students who are first learning probability. Is we can use this example. What is the probability of having HIV given that you were tested positive on a test versus what is the probability of testing positive given that you have HIV? We're dealing with two events, but their condition is reversed. And because of that, we'll get different answers to those two different questions. So with conditional probabilities, we usually use either a probability tree diagram or a probability table in order to understand it, because they're easier to illustrate, and it's a little bit easier to understand as opposed to using, let's say, a Venn diagram. So here we have a probability tree. We can look at the chance of getting heads or tails with a coin flip. And so here we have the coin flip, and we can draw an arrow to heads and an arrow to tails, and the probability of both is 0.5. We can add up the two and get 1. So here we can do another coin flip after that and see what the probabilities of us to get a heads and then a tails, or tails and then a heads. And in order to do that, we would just multiply across the branches. So probability of getting a heads 2 times in a row would be 0.5 times 0.5, which is 0.25. So you have a 25% chance of getting 2 heads if you flip the coin twice. And because you have a 25% of these 4 outcomes, if you add them all up, they'll equal 1. And here we can use conditional probabilities within the probability tree to make it a little bit easier to look at, and it's the same case. So they're all going to add up to 1, and to find the given probability, you're going to multiply across. And here you can actually use the multiplication rule as well to illustrate that. So here's back to the example of health insurance. Given that a person is poor, what is the probability of having no health insurance? So the probability of having insurance given someone is poor, this is how we calculate it. We're looking at the probability of those who have insurance and the probability of being poor, okay, which is 0.29. We're dividing it by the probability of being poor, which is this 0.09 plus the 0.29, which is equal to 0.38. So we're taking 0.29, dividing by 0.38, and we get 0.76. So given the respondent is poor, we're looking at this poor people. What is the probability of them having health insurance? So that is 76%. So given that they're poor, 76% of poor people have health insurance. So that actually sounds pretty good, right? And we can do it the same way that was using a probability table. Now we can also look at it with a probability tree, and we can get the same answer by multiplying across the probability tree and arriving at our answer. We could also look at another example. Given the respondent has health insurance, what is the probability of being poor? So that is the two conditions getting flipped, just to illustrate that they're not the same. We're looking at the probability of the insured, which is 0.88, and having this 0.29 over that, and that's 33%. So we just want to make sure that we don't get confused with flipping the conditions. And And the conditions matter because what you're conditioning on can drastically affect the probabilities of something. As we see here, the two flipped do not mean the same thing and they don't come up with the same answer. And here we're asking if having health insurance is independent of being in poverty, and how could we know that? And the answer is no, because if we took the probability of being poor and insured, it doesn't just equal the two multiplied together. So that means that we have dependent probabilities here, which makes sense because the likelihood that someone is poor can be dependent on whether someone has insurance or not, can be dependent on whether they are poor or not poor. So finally, we'll talk about relative risk. I gave that example earlier. It's a ratio of conditional probabilities. It represents the probability of an event given you're exposed to something over the probability of an event given that you're not exposed. So here we could talk about the probability of having insurance given that you're poor. And if you have a relative risk over 1, it means it's more likely to occur in the exposed group than the unexposed group. And if it's less than 1, it's the reverse, it's less likely to occur. And if it's 1, it means there's no difference in risk between the two groups. So if you have a relative risk of 4, it means the exposed group is 4 times as likely to have the event occur. If it's 0.5, they're half as likely to have it occur. So here's how we can calculate the relative risk of being uninsured given people who are poor. And we actually find, using calculating it, that it's around 4.8. So those who are poor are 4.8 times as likely to be uninsured than those who are not poor. There are some limitations to relative risk because it's an association. It's not causation. It's not, you're not proving anything that's causal. We actually don't do that in statistics. We can say there's a correlation, but not a causation. So those are some things to know, and that was the end of that lecture. So we flew by that quickly. That was a lot of material. If it was confusing, don't worry. You have the entire second module, which the entire module which came out tonight. So you can watch Ethan teach you this material as well. And we're going to have sections throughout the week, and you're going to have some quizzes. So by the time your next assignment comes around next week, you guys are going to be in great shape. Does anyone have any questions I can help answer? So feel free, if there's any questions, you're more than welcome to ask them now. I'm happy to answer any questions, or if you want to send any of us emails, happy to talk offline, or you're also welcome to post in the discussion forum. It's a great way to have some questions answered. I'll be around for a couple more minutes in case anyone has any questions on this material or anything course related. If not, feel free to enjoy the rest of your evening, and we'll be back next week with sections, and hope the rest of your week goes well. So someone, sorry, I'm just looking at the chat log now. So we have, if asked to calculate the joint probability, is it probability of A and B, or is it probability of A or B? So if you're asked to calculate the joint probability of the intersection, that would be the probability of A and B. Then we have another question here. Could you please show how to better use R to display the view or probability if possible? Yeah, so we actually have a number. We have codes that we provide for you on the course website to be used for the probability module. So I can briefly show you guys how to do that, but it might be more helpful for you to try the R commands that we give you on your own, and then we can discuss it more next week to prepare for the problem set. So basically, what the R commands that we give you do is we show you how to make those charts, the probability charts like these. So you can make either just a regular counting chart like this, a contingency table, or you can also make a probability chart. So that's basically what the codes that we give you for R in this chapter are, because there's not too much else you can really do with a computer program or with R in particular to really help you with probability, unfortunately. So this is one of the chapters where there's the amount of commands that we use are pretty light as far as the R commands. But take a look at the ones on the website that we give you, play around with them, and happy to discuss more about using R with probability next week. And I saw, Fatima, you said you had a question from mission 1. We can take a look at that if you'd like. So question is, among those in the lower class, what proportion survived the Titanic approximately? Okay, so we can look at that. I'll pull up R and we can look at this together. So I'm just loading up my R. It's taking just a couple minutes. Okay, so I've gone ahead and pulled up RStudio. Let's see if you can see. Yeah, you should be able to see that. And I'm going to go down and make sure that my Mosaic package is loaded up. So I'm just going to check off Mosaic. And you had a question regarding amongst those who are in the lower class, what proportion survived the Titanic approximately. So now that the Mosaic package has been loaded up and I have my Titanic data set loaded in and I have my code here for question number 13, I can run this code here and we can look here at this contingency table. Here we have the class up top, lower, middle, and upper, and those who survived, yes or no. And the question was, among those in the lower class, what proportion survived the Titanic approximately, right? So here's the lower class. So this is 100% of the lower class here. We can see that amongst the lower class that 26% roughly of the lower class survived the Titanic, and about 74% did not survive the Titanic. So by looking at this chart, we can determine the proportion of those who are in the lower class who survived the Titanic or not. How do we open up the code? So there's a code on the website which was called pset1rcode.r. What we can do is download that from the course website. So I actually went and downloaded that to my desktop here, and it's called pset1rcode.r. So all I did was click on it here, and that will bring it up here to RStudio. And then it actually gives you the R scripts for the different problem sets. And what we can do is for the given different questions here, we can just highlight the code that we want to run here in blue. So we just can click on it and drag until we've gotten the entire code here, and then hit run. And that will bring it down to the console, and that will run the command. I can show you if you're still confused where to find them on the course website. Okay, great. So it looks like you got it, Fatima. Does anyone else have any other questions before we sign off for tonight? Okay, so the question was, amongst those females in the lower class, what proportion survived the Titanic approximately? So okay, so here, based on the data set, what proportion of men survived the Titanic approximately, right? That was question number 12. Is that the question? So we can highlight this command here, which is going to tally by survived given gender. That's what this command is saying. Tally by survival data given gender, and the format is proportion. The data, it's telling R to use the Titanic data, and margins is equal to true. So we can run this command here, and we can see here that we have a proportion table with gender on the top being male and female. On the left, we have survived, yes or no. So the question is, what proportion of men survived the Titanic approximately? So we can look here, the amount of men. So we have, here's the men that about 20.5% survived the Titanic. Those were men, and about 80% did not survive amongst men. And if we look at the females, it looks like about 75% of the females did survive, and about 25% did not. And if you've ever seen the movie Titanic, I think they illustrate that, because as the Titanic was going down, they said women and children first on the lifeboats, and then the men were left with anything that was left over, but they gave preference to all the women and children on the ship as it was going down. Does that answer your question, Amy, on how to answer this question? Great. Awesome. Well, I'm glad that we got through the probability lecture together. It's a lot of material, and I'm glad everyone was patient and got through that together, and we got to answer some questions about the homework. So I hope that everyone has a great week, a great weekend, and best of luck with this next week. Let us know if you have any questions or concerns about the course material, and have a good night.